Mistake here. What is wrong with this equation for the speed of light? It's not requiring anything in the derivation. Derivation is fine. It's just looking at this. Physicists had a problem with it.
Did they think that you could get no, never mind. Yeah, I thought it had something to do with the radical.
Oh, not a problem with the radical. It's a problem with what is speed? How fast are you moving right now? What's your current speed?
0?
Is it?
Oh,
It's
yeah, it's
scale.
is it relative?
Yeah, because it's scalar and dependent on like a point.
Say, independent or dependent?
Dependent.
Dependent. Dependent on what?
A point. A reference. A frame of reference.
Yeah. Nowhere in here is there anything about a frame of reference. If Maxwell did not make a mistake, he's making the claim that the speed of light, or speed of electromagnetic wave, speed of light, is the same regardless of the reference frame. And late 19th century physicists said, that's clearly not the case. Because let's think about what happens if that is the case. Let's do the thought experiment. So right now we're going to pretend that the speed of light is the same regardless of the reference frame. I'll call this lab frame. Got a mirror on top, and I got a box here that's moving to the right at some speed v. It is going to shoot light out the top. From the light out the top, it's going to, since the box is moving this way, the light will have some component in this direction, and the light's going to come up, hit the mirror, come back down, and get back to the box. In the box frame, so you're sitting in the box. From the box's point of view, the light just goes up and back. There's my mirror. So I'm on the side observing it. I see the light go boom, boom. And you're in the box, you just see the light go up and down. The speed of light, let's go ahead and work our way into the official designation. C is typically the letter used. So if the speed of light is the same, well, this light is traveling from here to here to here. So it's going to be traveling, that's the distance that the light will travel. So C is going to be this distance. I'm just going to call this D sub L. Yeah. D sub L, so that's that plus that over time. And in the box frame, C would be equal to D sub B, which is just basically that there to there over time. D sub L and D sub B, clearly not the same thing. One of them is just straight up and back, the other one we got at angles. If the speed of light is the same in both cases, what else has to be true?
That the time is the same in both cases?
Say that again?
That the time is the same in both cases?
If the time is the same in both cases, that means that this distance and that distance have to be the same. Therefore, oh, you were so close.
I'm so close.
If we were making the claim the speed of light is the same in both cases, because Maxwell doesn't have anything about a frame of reference, then we are making the claim that d sub L over t equals d sub d over t.
Yeah.
I know the numerator's clearly not the same. Therefore,
The time has to be different.
yes. So close yet on the completely opposite side of it.
Yeah.
T sub L, T sub D. This says that time is not the same. And this blows their little minds. Yeah. Well, clearly Maxwell made a mistake because time can't be different to different people. In 1905, so this was 1870s or so. 1905, Einstein comes along and he goes, let's suppose Maxwell did not make a mistake. Let's run with that, see what happens. Actually, in 1905, Einstein comes out with 4 papers. One, he comes out with his theory of special relativity, which we're about to launch into, at least an introduction to it. Comes out with the framework for general relativity. Comes out with evidence for the atomic theory of gases. Comes out with statistical proof of it, and then the 4th one I could never remember. But those 3, the 3 that I did mention, any one of them could have won a Nobel Prize. But he did manage to get one Nobel Prize, and primarily because he was Jewish. Nazi Germany did not spring out of a vacuum. He was given a Nobel Prize for contributions to the theoretical physics or something like that. Just lump them all together. All right, so if we accept the fact, so Einstein comes along, he says that the times are not the same. So I'm going to change some notation here. So let's make this distance here h. And so therefore this distance here, let's see, light frame, I'm going to label this one t sub 0, that just plain t. Most textbooks will label this t prime, t and t prime, but I'll prefer t sub 0 and just t. So if this takes place in the time t, then this distance traveled here would just be however fast the box is traveling times time. If I look at this triangle, I know that this h, this is 1/2 vt, and so my hypotenuse would be the square root of h squared plus 1/2 vt squared. Pythagorean theorem. So the distance that the light travels in the lab frame is 2 times the square root of h squared plus 1/2 vt squared over time. And in the box frame, c would equal the distance, which is just 2h over t sub 0. Well, h is just like when we were deriving it, h is just some arbitrary value. So let's solve for h in both cases and then set them equal to each other. So down here, h is equal to 1/2 c t sub 0. Actually, just go ahead and substitute. Now I'm going to plug that into here. So I have c equals 2 times square root of h squared, which I now know is 1/2 c t sub 0 squared, plus 1/2 v t squared over t. So that is t sub 0, those are just t. We need to simplify this somehow, so I'm just going to multiply both sides by 1/2 t, and so I get 1/2 ct equals the square root of 1/2 c t sub 0 squared plus 1/2 vt squared. Square both sides, so I get 1/4 c squared t squared equals 1/4 c squared t sub 0 squared plus 1/4 v squared t squared. Take a moment to let that sink in and to point out any mistakes or ask questions. Questions, comments, or concerns? One quarter drops out. Multiply everything by 4. I'm now left with this. So now it's just a matter of what form do we actually want. So what I'm going to do is I'm going to get all the t's together and the t naughts together. Well, there's only one t naught. I'm going to get the t's together. I'm going to solve for time. How does the time differ? So I have c squared t naught squared equals c squared t squared minus v squared t squared. Because I know the form that is traditionally presented, I am going to now divide both sides by c squared. So I have t naught equals t naught squared equals t squared minus v squared over c squared t squared. Factor the t squared out, I'm left with 1 minus v squared over c squared. I'm going to take the square root of both sides, so t sub 0 equals t times the square root of 1 minus v squared over c squared. And then the last little bit, it's just formatting, solving for t. So this is the time in the lab frame, so you're on the sideline, is equal to t sub 0 divided by the square root of 1 minus v squared over c squared. That is the traditional form. Let's see what the implications are. Let's say that the box is traveling at 0.9 times the speed of light. And it is set up, the mirror is far enough away that from the box's point of view, 1 second passes. If we plug and chug, we can now figure out how long from the lab frame, how long it's going to look it takes to go. And so t equals 1 divided by 1 minus 0.9 squared, which is 1 over 0.19, which is something. Is that the 7.09?
5.263.
5.263? Let's make sure, see, that's 0.81 last. Yeah, I'm feeling comfortable enough with that. Seconds. So 1 second passes for the box's point of view, but over 5 seconds passes for the lab point of view. Matter of fact, the faster you're going, the more the distortion. So if you rush on your way here to school, your internal clock, the watch, everything is going to slow down. This is not just an illusion. This is physically, time does not pass the same. However, well, not a however. Now, I talked about the physicists looked at what Maxwell did, and they came and they did. Physicists looked at it and said, no, that's not right. One particular physicist, Lorentz, came so close to coming up with special relativity, but he refused to make that last leap of saying time is not the same. Lorentz spent a good chunk of time, decades, trying to figure out why it appeared to be time different. That was a bizarre sentence. Why it appeared that the time was different. And so he jumped through hoops trying to figure out, because there's also something known as length contraction, and there's also various other distortions. And he thought it was all an illusion and tried to come up with justification for it. But alas, Lorentz. So there are a number of, Lorentz's name is going to pop up a number of times. Just be aware that he doesn't get credit for special relativity because he was looking for something different. Now, what impact is this? This is known as time dilation. What impact does this have on your life? Well, actually, in the modern times, quite a bit. GPS satellites, they're orbiting the Earth. They're traveling at a couple thousand miles an hour or meters per second. Even though they're not traveling anywhere near the speed of light, it is just enough that if you don't correct for special relativity, it'll get thrown off by, if I'm going off memory on this one, 30 feet a day.
Wow.
You also have to take general relativity into account, and that also throws it off by a little bit. So GPS satellites have to take how fast they're going into account. So Einstein comes up with this in 1905, along with the other papers. General relativity, so special relativity assumes what's known as an inertial frame and inertial frame. In other words, constant acceleration. Sorry, badly worded, constant velocity. Wow, big difference. So we're dealing with the box is traveling, and it's traveling at a constant speed, constant velocity. General relativity goes, suppose it's accelerating. How do we deal with it then? I'm going to lay out the principles of general relativity, and it'll basically deplete my knowledge of general relativity. I took a general relativity course. I've told this story before, haven't I? General relativity course I took in college.
I don't know.
Or grad school. Bill Baird, who's now teaches at Savannah State or somewhere in Georgia, wanted to take it. And so he talked, conned enough of us into taking general relativity so that they could have a class. My goal on the first test was to understand the question. I did not succeed. I've told you the Peter Course story. Okay, so you've heard it, maybe not. Anyway, it was that class. Just the quick reference. Teacher mentioned the theorem of Peter Course. I'm going, Peter Course? I don't know who that is. And he looks at us and we like looks on our faces apparently. He goes, you know, Peter Course. A squared plus B squared equals C squared. That was my attempt at the Polish accent with which he spoke at the time. Ah, okay. I had that guy from 2 different classes. I put a sign up. I was doing part-time teaching high school at the time, so I put a sign up in the back. His name was Pavel Mazur, never forget. Just, I did not want to become like that. Probably have my moments. All right, general relativity, I guess we'll pick that up next time. And that'll take a couple minutes.
This is crazy.
It is. More than once over the years, I've had students, as we get it deeper into special relativity, they go, no, this doesn't make any sense. Not in the way of, I don't know what you're talking about, in the way that this completely conflicts with my worldview,
Yeah.
and it will. We are not going to delve too deeply into special relativity right now. This is the point where it flows so naturally, and I generally jump into special relativity. Then I've had a student in the past who, after here, went elsewhere, went to NC State actually, and sent the word back of, you skipped AC circuits, would you please do AC circuits? It would have been really helpful to have done that beforehand. And so we'll just wrap up a couple thoughts on special relativity and then jump back and then hit special relativity again. But special relativity, my favorite topic, just because it is so mind-blowing.
Wow.
Twin paradox, we get the train example where only one of them can be right, but it looks on the surface like both of them are right.
Cool.
Some fun stuff.
Mind-boggling.
Wish I was smart enough to understand any of this.